Hello everyone, we'll continue the discussion of clay mineralogy. I have already told the basic, but we'll revise quickly whatever we have done and then we'll go ahead for further information. So these basic blocks, you have seen that it is silica tetrahedron and then alumina octahedron. 8 faces they have, that's why octahedron. 4 faces they have, that's why it is tetrahedron. The oxygens at the base are called basal oxygens, whereas oxygen at the apex are called apical oxygens. Here it will be OH. Right. Now we'll see further how it will be. Yeah, these blocks, the tetrahedron blocks, when they join one to the other, it will be like this. This is exactly from the top. If you try to see, this is seen at the center and these three will be seen at the corners of a triangle, and then a molecule of silica tetrahedron joins with the other, and so on. They'll make hexagon combination, and this structure continues for millions of such star-like structures, because it is quite microscopic. So actually when we see with our bare eyes, it will be not seen, but microscopically when you see the structure of the clay, it will be looking like this. So this is a microscopic view of the clay. Okay. Now how the layering is done, that is, look at that. What I am trying to show there is this layer, which is the top layer, one layer, and there is another layer. There are two layers actually. Okay. Here I have alumina octahedron on the top. This is represented by a rectangle, whereas silica tetrahedron sheet will be represented by a trapezium. Such sheets will be joined together by a weaker bonding, and this bonding itself makes number of clay minerals. Of course, there will be one-to-one clay mineral. This is called kaolinite, one-to-one clay mineral. This is called two-to-one. Two silica tetrahedron sheets are sandwiching alumina octahedron sheet. Okay, that is alumina octahedron sheet. Okay, now it is like this, right? The same sheet is shown in another pictorial way. The top, this pyramidal kind of things will be there on there, and then these octahedron sheets are here, and then one more layer of tetrahedron sheets, and these are basal oxygens which are shown on the top as well as at the bottom, right? So here there is an layer to layer, and then there is a space in between which is called as interlayer, wherein there is a possibility of entrance of water or positive ions, right? To what extent the positive ions will be entering, which is called cation exchange capacity, right? So this negative charge is because of number of reasons. Of course, we'll see in further slides also. Molecular and structural form, we have seen this when it comes in 6 sheets. When they come, it will be like this. This silica tetrahedron sheet will be represented by a silica sheet, which will be a trapezium like that. This is silica sheet. So when we write or present it, you have to show it in this manner, because we cannot draw all these kind of pictures. Alumina octahedron, right? Here what happens is this particular shape, of course it is a parallelogram kind of thing, but it is represented as a rectangular sheet, which is a gibbsite sheet. It is called silica sheet, and then there is a alumina octahedron sheet which is called gibbsite sheet. Now here you can just see, here it is 2 to 1 clay mineral is shown, tetrahedron sheet, octahedron sheet, tetrahedron sheet. This is one layer. Like that there is one more layer. So in between the layers we have interlayer, wherein adsorbed cations and then water will be entering. Now if these two layers are not getting attracted strongly, there will be a lot of water which will be getting into that space. If they are very strongly attracted, then there is lesser possibility that water can enter in between that space. That is the point of interest. Okay, here one tetrahedron sheet, one octahedron sheet, the same thing is shown, 1 to 1 clay mineral it is called. Here 2 sheets of tetrahedron and then 1 sheet of gibbsite, right? That is called 2 to 1 clay mineral. Okay. Okay. Now when we write, we should write it this way. This is 1 to 1 silicate. Example is China clay. Kaolinite, it is called as. Now how it comes? It comes in a sheet form, right? I think I have, yes, this particular layer is shown like this. Actually that is the basic building block as far as kaolinite is concerned. Okay, there you can see that that is the one, and then the same thing again shown as one single block. So this is called basic structural unit. The symbol for one combination, 1:1 clay mineral is this. Now such number of layers will be there. As I told you, in between there is an interlayer, and here in case of kaolinite, this is bonded together by hydrogen bonding, a very strong bond. Because of that it is stable, water cannot enter easily, right? The thickness of one such layer is of order of 7.2 angstroms, but when it comes in existence, the sheet will be having sufficiently good number of such molecules will be together, but still the size will be, thickness will be 100 to 1000 angstroms. Such sheet can be visible, right? And then lengthwise, if you see, it will be 1000 to 20,000 angstroms lateral size. Now here, specific surface area, which I have explained you in the last class, has got 15 meters square per gram, and then it will be having a negative charge in the surface of the order of -1 to -15 centimole per kg. Okay, so the point to be noted here is specific surface area, that is 15 meters square per gram. Okay. Now the same thing is shown in another form, right? That is one layer. The same layer is shown as a building block there. The same thing is shown there. Like that it continues. The number of layers will be there. Layers are electrically neutral because there is little cation substitution in the structure. Layers are held together by hydrogen bond, non-expansive, right? In between the layers you have these hydrogen bonds. Charges are unsatisfied only on broken edges and surfaces. So you can just see here one oxygen atom is hanging, otherwise the others are attaching one the other, right? Okay, we'll see further. In the same picture, here 2:1 clay, the next clay, first one was kaolinite, 1:1. Now this is 2:1, which is called as illite. Now the basic building block symbol will be like this, because it is a 2:1. Okay, so that is the one basic structure or fundamental building block. The same thing will be shown there. Again, that one is taken as one layer. Now such layers will be getting added number of times, right? Now existence, I mean actual size of one layer will be of the order of 10 angstroms, but in actual existence there will be number of them, and they exist in the thickness of 50 to 500 angstrom, and lateral length will be of the order of 1000 to 5000 angstrom units. Yeah, most important thing here is the specific surface area. Now it has increased. You can just see here 80 meters square per gram. That's how the surface area becomes. So it is becoming too small in size. Because of that, the specific surface area has increased. Okay, now what happens is, in between these two layers, how these layers are attached. Here you got cation bonding. K plus, potassium plus, non-exchangeable bond is weaker than hydrogen bond but stronger than water bond found in montmorillonite. So this illite is in between a kaolinite, earlier we have seen, and then there is one more which is montmorillonite. So this is in between, right? That's why earlier specific surface area, if you remember, it will be 15. It was 15 meters square per gram. Now it is 80 meters square per gram. Obviously, a lot of surface forces which will be coming into picture. Okay. So here the last one, montmorillonite is the clay. Montmorillonite is the clay. This is also 2:1 silicate. Right, primary constituent of black cotton soil or bentonite clay. That is what it is commercially called, bentonite clay. Thickness of each layer, combination of silicon, aluminium, silicon tetrahedron sheet will be approximately 9 to 10 angstrom units. That is what one layer is shown here. Aluminosilicate layer negatively charged on the surface. Okay, the same layer is there, but in between you will be having exchangeable intermediate cations and water. So this particular space in between the sheets has got a lot of exchangeable cations. So net charge deficiency because of water and exchangeable cation can enter and separate the layer. So what happens is, one layer and another layer in between, when the water enters, it expands, right? So that is why the clay, like black cotton clay, expands whenever water comes into picture. To the tune of 30%, the volume will be increased. Okay, when actual existence comes, it is in the thickness of 10 to 50 angstrom units. Look at the size, very small, right? And length will be of the order of 1000 to 5000 angstrom units. Here, this is very important information. Look at the specific surface area, 800 meters square per gram. Too much, right? Per gram. Gram means such a small quantity, but when it is spread with its surface area, it can cover an area of the order of 800 meters square, too much. And then because of that, the concentration of charge on the surface is minus 80 to minus 150 centimole per kg. Okay, that is the space which is the most important space where water and cations will be entering. The same thing is shown once again. The important points to be noted are it shrinks and swells a lot. Montmorillonite has got that kind of property, or in general clay minerals, but this has got too much of it. It can expand up to 30%. It has got the maximum surface area. I told you it is around 800 meters square per gram. Okay, here at one point all the three minerals are shown. This is kaolinite. You have got tetrahedral, octahedral, one sheet, another sheet in between. You have got a interlayer, right? So this is alumina octahedron sheet, blue, silica tetrahedron sheet, green, which is shown as a trapezium, whereas this is as a rectangle. Now this is 1:1, because of that only 1:1 sheet is there. Now when it comes to illite, which is a 2:1 non-expansive, so 1 nanometer thickness, or I told you 10 angstrom units, right? Here you have got a K plus ions in between, and because of that it is slightly stable. Okay, then there is a clay mineral by name vermiculite. It's also, all of them are 2:1 now, so moderately expansive, because water molecules and cations will be entering into that. Now in case of smectite, highly expansive soil, there will be too many water molecules, and then cations will be entering into that. So chlorite, again non-expansive, it is a hydroxyl sheet will be there in between. So in montmorillonite, it has got too much of thickness of water. Okay, here we'll be starting slightly different thing. Primary valence bond and secondary valence bond. What it means, how this charges etc. come into picture. That's what we are going to see. Just we'll go through. Primary valence bond is intermolecular bond, right? It is a bond between atoms in a molecule. These are strong bonds, primary molecules. Means suppose you got H2O, right? The bonding between H and O, it is an ionic bond, you might have studied earlier. It's a very strong bond. So it is bonding between the atoms in a molecule, primary valence bond. Secondary valence bond is the bond between the atoms of different molecules. Okay, so here what I mean is that interlayer, whatever we have seen earlier, that bond we are talking about, right? Secondary valence bond is the bond between the atoms of different molecules. It is intermolecular bond. That is intramolecular bond. Here it is called intermolecular bond, and these are obviously weak bonds. Now secondary valence bonds are because of two factors. One is van der Waals forces, orientation effect it is, otherwise it is a hydrogen bond. Now here what is shown is H2O, neutral polar system. If it is a H2O, now plus and minus are equally distributed, because of that it will be neutral. But in actual existence, H2O comes in this format, means oxygen hydrogen atoms are slightly on one side. Orientation is like this. The angle between the two uh, hydrogen bonds is 105, not 180 degrees. Had it been 180 degrees, then it would have been a neutral charge. Now this itself, this molecule of water itself is shown like this. So on one edge, charges are interchanged. Anyway, it is plus here, so that's why one edge is plus. Here minus here, that's why one edge is minus. So the molecule is, the water molecule is polar, in the sense it will be having a negative pole and then a positive pole, like a magnet, right? So it is not a neutral molecule, so that because there are two poles, the water molecule is called dipole molecule, right? Di is two poles, two poles are there, because of that it will be dipole molecule, water is called. Now how this plays an important role in clay minerals, we'll see further. Okay, the force of attraction between oppositely charged ends of permanent dipoles is called orientation effect. Now when we place one H2O, another H2O, this is called orientation effect. When non-polar molecules become polar in an electrical field, it is said to be an induced dipole. Okay, on its own when it exists, it is a orientation effect and then a permanent dipole. Because of electrical field, when it becomes instantly, because of the inductive effect, it will be induced dipole. Now the intermolecular forces due to fluctuating dipoles is called a dispersion effect, right? Sometimes it shows the charge, sometimes it doesn't show the charge. Okay, now hydrogen atom oscillates between two oxygen atoms. Yeah, this hydrogen atom will be sharing its charge with this oxygen or that oxygen. That's why there will be a bond, right? Oxygen, two oxygen ions of the water molecule. Okay, next is this is called diffuse double layer. I'll explain you what happens here. This is a clay mineral which is shown here, and there is a molecule of, let us say, water is there. Molecule of water is there. All these are molecules of water standing by the side of, or attached by the side of clay mineral, which is negatively charged. Hope you can understand, right? So when you got a clay mineral which is flaky, on its surface you got negative charges, and when water molecule comes, it stands like this with its positive side, positive pole on this side, negative pole on that side. So like that, number of water molecules will be standing with plus attached to the clay mineral, minus on that side. Now when the next molecule of water comes, obviously again it stands like this with plus here and then minus there, and then one more layer of one more molecule of water comes, it will be plus and minus, and then one more layer, one more molecule, and then one more molecule, like that this layer continues, right? Because this is very strongly attracting, right? Depending upon how much this charge is, that much of ions of that much of molecules of water are attracted strongly towards it, and this nature makes this interlayer thickness more, right? Maybe water will be entering, maybe cations will be entering in between, and this layer thickness, when it becomes more and more, the soil becomes expansive, or it bulges up. Okay, the capacity of attraction of these molecules is shown here. Now this is the surface, yeah, the same reference is shown here. As you move away from the surface, the attraction between the clay mineral and the water molecules or cations will be decreasing. So electrical potential will be continuously dropping. It is a distance from colloidal molecule. So as you go away, here you can just see here, as you go away, I'll choose the pointer. Yeah, as you go away from the molecule, the attractive force will be getting lessened and lessened. That is what is shown here. The same thing again here. Here cation getting attracted will be very large, nearer to the surface of clay mineral. It reduces, and because there is an existence of negatively charged surface, it can try to attract even positive charges, that is anion attraction. Even that will be there, but quite less, and both of them come and then join there. So this is the distance from the colloidal surface or clay mineral, right? Hope you have understood. So because of this, what happens is clay mineral, look at this clay mineral, and there is a lot of water around it. I'll try to choose the different color. There is a lot of water, number of molecules or layers of water are there. So if I show one layer of water molecule, you can just see here. So one layer of molecule, next layer, and so on. There is a lot of water which is around. Now when we have next molecule, next clay particle, let us say there is one more clay particle, let us say there is one more clay particle, like that, and they will be having their own water layer attracted towards it. So this will be having its own water layer around it, this will be having its own water layer around it. So like that, a number of particles of clay will be there, and then with a lot of water surrounding that. Now when you have got something like this, when you try to push one molecule or one particle of clay, obviously what happens is this molecule easily slides on the surface of water without much of problem. So that's why the clay exhibits that plastic property. So when you bend the clay, it doesn't break, it just nicely bends without much of a problem, only because of this. So to say, what I mean here is the plastic nature for clay, or in the presence of course water, comes only because of this particular reason. If you can understand itself, well and good, right? Because the clay particles are negatively charged, there will be a big thickness of water which is surrounding on that. So this is the case with all the clay minerals. So because of that, whenever there is some kind of shearing force, it easily can sustain that shear, but just by sliding of clay mineral particles one above the other easily without much of breaking, right? There is no crack. When you bend it, it bends and then takes that shape. So this is called plasticity, or plastic nature of clay in the presence of water. Without the presence of water, clay will not be acting as a plastic material. When it is dry, you will not be able to make a bending or plastic nature will not be there. So the water, because of its dipole nature, plays an important role to bring plasticity to soils. Okay. Okay, what is isomorphic substitution? I can just see here. We'll read it out. Ion substitution in the basic mineral structure. That is, we have aluminum and silicate. Aluminum plus 3, and then for silicate plus 4 in tetrahedral layer, octahedral and tetrahedral layer. Now Fe2 plus or Fe3 plus, manganese, magnesium, aluminium in octahedral sheets. Okay. Now this results in change of imbalance, permanent change. Okay. Now how it happens, I'll show you here. Isomorphic means what? It is having the same shape. Refers to the substitution of one ion for another ion without changing the morphology or structure of the soil. So this is an important definition of what is isomorphic substitution. I'll show you that picture also. Yeah, here silicon is there, oxygen atoms are formed. Now this silicon is removed and replaced by magnesium. Structure remains the same. Look at that. But what has happened is, this was plus 4, this is now only plus 2. Because of that, this is more negative. It will be minus 2. So net charge will be minus 2. Because of this, what happens is, the structure is not changing, but the charge is, negative charge has enhanced. So that such kind of substitution is known as isomorphic substitution. So replacement of one atom by another of similar size is important, without disrupting the crystal structure of the clay mineral is known as isomorphic substitution. Here also refers to the substitution of one ion for another ion without changing the morphology or structure of the mineral. Okay. Substitution of cations in octahedral sheet is common and is known as isomorphic substitution, which leads to different clay minerals. Right? You have seen those clay minerals, elite, and then what is that, kaolinite, and then montmorillonite. Of course there are vermiculite, and then the other chlorite minerals are also there. The important ones are kaolinite, elite, and the most important is montmorillonite. As far as agricultural point of view is concerned, this is important because what happens is this water will be able to carry all these ions, that is nitrogen, potassium, calcium, etc., and that will be taken up by the plants, right? The bad part is even pollutants will be caught on to the surface of the water, water of the clay mineral. That is the bad part. So environmentally, agriculturally, and human health, all these will be getting affected because of this existence nature, right? Over a dozen of clay mineral exist without a different combination, with different combination of silica and gibbsite sheets, and with the different isomorphous substitutions. But in engineering, we study kaolinite, elite, and montmorillonite. A replacement of one atom by another of similar size without disrupting crystal structure of the clay mineral is known as isomorphic substitution. Okay. The negative charge comes because of what reason? That is what is important. Here also it becomes negative. Here also there will be negative charge on the surface. Okay, this will stop here. Thank you.